let me just go ahead and get this DVD stuff started here, and then I'll give you some updates on a few items. What we're going to talk about today in today's session is the sine and cosine functions. Now, we're going to try to split this into 4 different segments. I'm not going to exactly follow the titling I have here, where we talk first about the sine function, then the cosine function, then reviewing transformations. Do you remember what those are? They mean to do what to a graph? Stretch and squeeze, flip it upside down, that kind of thing. Change the shape of it, right? And then move it left, right, up, or down. Okay? Very important in trigonometry. And many of you are probably a little rusty on this, so we'll make sure we go over this. And then we also want to then talk about practicing graphing our trig functions, sine and cosine, using transformations. Now, I probably will I'm just going to split this class session into these 4 segments. It may not exactly follow this order, because I think it'd be useful for us just to kind of mix these things together as we go. Okay? Now, aside for you folks in the class, that 25-point first quiz, which covers the very first section, 6.1 of the book, and then 8.1, and just a very little in 6.2. That's not due till Wednesday night by the time of closing in the Resource Center. And then the homework quiz 2, I'm going to prepare that later today, and it won't be due until this Thursday at 5 p.m. Okay, and it'll be homework problems, a few homework problems from the second week's homework. Okay? So let's go ahead and kind of pick up where I sort of left off in the last session. Here's what we were doing, if you remember, okay, after the holiday. If we take our unit circle, and you should be pretty good with that by now, I hope, of being able to understand what happens there. And if we take a standard angle, drawing's not too good here, standard angle, positive angle shown, then on our unit circle with a hypotenuse of 1, this is a reading of the cosine of the angle, and this is a reading of the sine of the angle. The x and the y readings there. Where we were the other day is we were talking about the variation that occurs for the sine readings. So the sine of an angle is going to vary between the y values that you see on this unit circle, between -1 down here and +1 up here. They're locked into those values, rising and falling, between values of -1 up to 1. -1 to 1. You should be comfortable with that. And I think what I want to do on the board here is actually pick up where I sort of left off, as I said in the last session, and I want us to translate those y values that occur as you let the angle change onto a graph that shows if the angle's changing this way as our independent variable, what are the values of the ratio, the sine ratio. Here's a way of thinking of it. If I took a little flashlight and shined it this way over onto a screen over here, over onto a screen where the y-axis is, you would see, if you started with your angle at 0 degrees, you'd see at 0 degrees, we would see the light image on the screen right here, wouldn't we? And then as this angle grows towards 90 degrees, the light is going to shine higher and higher and higher until it gets up to a value of 1. If you continue letting that happen for larger and larger angles, you can see it rises to 1, it then falls back towards 0, and then it goes negative on us down towards -1. So translating what happens with that height of that shadow varying between 1 to -1 onto a graph, what's going to be important for us is to note these key locations look something like that for the different angles. And we're going to see at 0 degrees, the sine reading is 0. When you get to 90 degrees, you're up here at 1. When you get to 180 degrees, we're back to 0. When you get to 270 degrees, we're down here, -1. Once you get this, it's easy. But until you do, until you understand it, it can be very confusing. And then finally, when you get back to 360, the shadow or the projection of the light is here. At 360 degrees, it's back to 0. What we briefly did in the last session, in addition to this, and what a common mistake people will make in drawing a sine graph is they'll draw a straight line, bunch of triangle-looking things here. But does the sine function grow linearly, like a straight line? No, it's on this curved, it's on this circular shape here. And so as I mentioned last session, is this thing takes off and climbs very quickly in here, near 0, as you let the angle change. It's rising quickly, relatively speaking. And when it's up here near 90 degrees, the angle's near 90 degrees, it's kind of hovering up in here near 1 for a while as the angle changes. You with me on that thinking? Okay. And then similarly down, when you're over here near 180 degrees, it's taking off, it's moving through 0, it's coming down to 0 quickly, and then it's going negative and pretty quickly heading on down as the angle is changing near 180 degrees there. It's moving quickly, the sine reading, the y reading. And then again, it's hovering down in here. It's hovering near -1 in value. Now, if you don't, and you're not going to ever see a description like that in a textbook, in a trig textbook. What you will see, though, in a trig book, and it's in section 6.2 and then 6.3 of our book, is if you take those 16 angles we've studied over and over and over again, if you split 90 degrees into thirds, you're on 30-degree increments there, 30, 60, 90. And then you can keep on going every 30 degrees, and you can click your way across here and very neatly draw that even on a whiteboard, right? And we know those trig values, those trig ratios. When you're at 30 degrees, you're already up at a half, aren't you? And that's more than if you were, it would be higher than if you were a third of the way over towards 90, you'd only be up a third normally on a straight line. You'd only be up at a third of the height. Okay, then when you get to 60 degrees, you're at square root of 3 over 2, which is 0.866. See if I can get that on there, 0.866. And here's 0.5. And then if you happen to be at 45 degrees right in the middle there, you're going to be at what value?
0.707.
0.707, square root of 2 over 2 is 70% of the way. 70% of the way. And so it actually forms a nice smooth curve coming up through there, better than I'm drawing, right? So that is the first part of this function. Notice it passes a vertical line test. Passes a vertical line test. A nice clean looking function. Then, because of the symmetric character that we have already seen through these ratio values, once you go past 90 degrees here, those values start falling towards 0 in the same way that they were growing over here. So once you get this first segment, we should be able to then draw that segment from 90 degrees on towards 180 degrees. Look at this. This is kind of nice. We've been practicing for several class sessions what the trig ratios were of those 16 angles, right? And we've been seeing it coming from this picture of the circle, right? And we got only 5 numbers to deal with, right? 0, a half, square root of 2 over 2, square root of 3 over 2, and 1. And then the negatives of those values, okay? And we've been seeing it from this. What you can now start to see over here is you can see those as locations on here. Like, what if I'm at 150 degrees? If I'm here at 150 degrees, you are going to be right here at 150 degrees. Let me get a decent marker here. We're going to be up at exactly 1/2, 0.5. So you can see it as a point on an actual functions graph instead of using this unit circle to image it. Right? What happens when we go past 180? Same kind of behavior going on for those y readings, being our sine values shown here. And similarly, past 180 degrees, coming back up towards 0. I'll do that with my fingers. -1, negative square root of 3 over 2, negative square root of 2 over 2, -1/2, and finally back up to 0. And that's going to reflect or show itself in here in that portion of the graph. There is our first trigonometric function. Y equals sine of theta. Does this graph continue past the 360 degrees? Yeah, keeps on rolling, doesn't it? And continues to repeat itself. Continues to repeat itself. What if we chose negative angles? Negative angles on this graph. Wouldn't they just plot back over in here? And keeps on going negatively. So notice, this is the first function you've seen in math that actually starts repeating itself after a certain period of the independent variable, or a certain cycle of the independent variable. It's called a harmonic model. A harmonic model. Similar to a spring bobbing up and down. Similar to the tides rising and falling. What I like to joke around about, what happens in this country if you'd stick your finger in a wall socket? The voltage is going up and down in an alternating current, and you get zzz, right? Okay, hopefully you don't do that because it's not a healthy thing, okay? But that's an alternating current. The graph looks very similar to this, very similar to this. Okay, so there's our first trigonometric function. Notice, why do we call it a function? It passes a vertical line test, does it not? Passes a vertical line test. What's the domain of this function? Any angle is possible, isn't it? From positive angles, negative angles. So from negative infinity to infinity. What's the range? The output values, right? The output values rising and falling between -1 up to 1. And we always rate these smaller to larger. Interval notation is what we're using frequently. Does the labeling here have to be like this in degree measure? No. Okay, huh? Could be radian measure, like Marty said, couldn't it? Radian measure, just as well. And that's where you, if you use your calculator on this, you would put your calculator in either degree measure or radian measure, and you'd set up a viewing window with your calculator that you wish to see, and you would set up your viewing window, and you would then put your scale marks probably at pi/2 values if you're in radian measure for your scale marks on your graphing calculator, or you probably put 90 degrees for your scale marks, okay, if you're in degree mode. And how low would you set your graph? The bottom of the screen on your calculator.
1.5.
Yeah, I'd go negative more than the minimum value. I'd go down maybe minus 1.5 or minus 2, and then up to the top here, maybe a plus 1.5 or 2 on the bottom and the top for a viewing window. Okay? Not too bad. Okay? And one way you can think of it is the way I described the flashlight pointing horizontal here, and then you pick up where the height is, and then you plot the various data points there. Okay. You could also build it from a table. I've mentioned that before. So we could build a table of values where we put in theta, and we have it calculate for us the sine of theta. And what I might do, and I actually think I'll grab the calculator and show you in a second, I'm going to go ahead and put the calculator in degree measure, degree mode, and I'm going to put 15-degree increments here, and I'm going to start at, say, minus 90 degrees, and then it would be minus 75 degrees, minus 60 degrees, and it's going to work its way through 0 degrees, and then it would continue on in increments of 15 degrees. And why did I choose 15 degrees? Anybody know? Other than just potluck?
30.
Because it happens to be a multiple of a factor of 30, and it also is a factor of 45. And 90, and 180, etc. So it's going to show all of our trig ratios of our 16 familiar angles, as well as some other data points there. So let me go do that real quickly for those who aren't familiar with a calculator. And this is kind of, in trigonometry, this is kind of like when you were in algebra, where you might have been first exposed to something like x cubed. You see a table of values, and then you generate a picture of it, okay? And then you learn it and memorize it, and then it's just part of your collection of elementary functions, right? Remember doing that with x cubed? So this is kind of analogous to that at this level in this course. So with the calculator on, zoom in and make the screen nice and large. And I'm going to go to mode, and I'm going to make sure I'm in degree mode here with the calculator, which I am. And then I'm going to go to table set, and I'm going to start the table at negative 90. And you can take notes with the calculator. When an instructor is doing a demonstration using technology, I would suggest you take notes, and then if you have extra time, is go ahead and jot down or see if you can punch along, but primarily take some notes so that you could go back to your notes and quickly duplicate the demonstration. What increment do I want to put here on my table? Starting at minus 90 degrees. 15 degrees for my increment. And then I need to go to y equals, and I'm going to put in here the sine of angle x. Sine of angle x. Excuse me?
What did you put as the table?
Second window.
Okay, table set is on the window key, and I start with minus 90, negative 90, and the increment is 15. Delta, the change in the table, is 15 degrees. Y equals is this, and at this point now I'm going to look at the table, and so that is using the second key or the shift key on the graph key where it says table, and you're going to see our familiar values at the familiar angles. So over here are the y values at minus 90 degrees. Think unit circle, folks. Mentally think where minus 90 degrees is on your unit circle, and think of what the sine reading is on that unit circle. It's -1, isn't it? And then think if you were at negative 60 degrees. Negative square root of 3 over 2 on the unit circle. See how this ties together? The values in the table tie together to you mentally thinking of where the angle sits on your unit circle, where the terminal side sits. And then here's your negative 45 degrees sine reading, negative 30, here's your 0. And then now for positive angles, I'm going to just move down here a little ways. All right. Now here's something you're going to love. If you remember it from algebra, look at this. Here are positive x values shown here, and here are negative x values. So we've changed this, jumping between these locations, we've changed the sign, we've changed the positive or negative character of the x values, right? Positive x versus negative x, right? Look over here. Look what's happening to the y values. They happen to be symmetric, but they also happen to be opposite in sign. What kind of a function do you think this exhibits from the table? What'd you say? She whispered odd. That's true. It's an odd function. It's an odd function. Now let's come back up to the board and look at the sketch and observe that if I continue to draw this graph to the left for negative domain values here, right, we're going to see that every point over to the right here has a point through the origin and out the other side that is symmetric to it. Symmetric to it. Now here's, a lot of you had college algebra from another instructor. Those who had me last term, well, the proof in the pudding is if you remember that stuff or not is the hard part. So let's just go back real quickly. You're all real comfortable with x cubed. And let me call this f of x. And I just want to quickly review this property with you of something that's called an odd function. If I would take a location x here, then this is f of x as the value of the function. It's the height on the graph here, is it not? If I would go symmetrically over to the negative of x, I would have this height, or the output value right here, would be f of negative x. These output values are identical, aren't they, in magnitude? But they are opposite in sign. This one's clearly positive, this is clearly negative. So if I took the opposite of one of these, it would be equal to this other one over here. This is what we have learned is the definition of an odd function. Definition of an odd function. Everybody okay with that? So now, related to trigonometry, with this new function we've just developed here, observe that the opposite of the sine of angle theta is equal to the sine of negative theta. That's a property that I did not get to earlier with you folks. I like to develop this property by looking at the graph instead of just memorizing something. Okay? Can you see this information? Can you see this statement? Can you see this statement from the unit circle over here? It's a big question. Okay. Here is the sine of theta off of our knowledge of the unit circle. If I instead went to negative theta, where would it be on this picture? It would be right down here, wouldn't it? Wouldn't it be down Let me erase the cosine. Wouldn't it be right here? Wouldn't that be that measure? And look at these y readings. This is the sine of negative theta right here. This value and this value are identical in magnitude, aren't they? Because of the geometry. But notice they're opposite in SIGN. One's the opposite of the other. Right? So if I take the negative of this value or opposite of this sine reading, that's going to be the same as this one, which is this statement right here. It's not hard once you see it. It's not hard once you see it. The important thing probably that you want to carry with you as you move on beyond this course into calculus is that the sine function is an odd function. Sine function is an odd function. So, if I said the sine of, what if I had the sine of negative 15 degrees? The sine of negative 15 degrees. And I knew that the sine function was an odd function. See, if I know it's an odd function, and we have 6 trig functions to deal with, if I know the sine function's an odd function, then the sine of negative 15 degrees is going to be the same as, yeah, it's going to relate to the sine of 15 degrees, but it has to be the opposite of that one. And you can see this in our table. So let's go back to the calculator and observe what we saw on the table. At 15 degrees, here's the sine of 15 degrees. And if I go to the negative of 15 degrees, the sine of negative 15 degrees is this value. So if I took the opposite of one of these, I would have the other one. Okay. That's going to take a little bit of practice for some of you. Okay. Let's go on with this. What I'd like to do is I think I'm going to go ahead and end this segment. Okay, let's go ahead and end this segment so it doesn't get too long in the digital file, and then we'll talk about the cosine. So I might be able to stick to this segmenting that we have here.